So I was thinking that we should implement a CPU.run method. And in this run method, we want to fetch the opcode, at least the data in memory, that is pointed by the program counter register. Next, we want to decode, number 2, decode the fetched opcode. And figure out what to do, right? So there's the regular opcode, or there could be the 0xCB one. Then we want to either increment the PC by some number of bytes. Basically, how much we have fetched, right? The question I have is, do we just fetch opcode, or do we fetch opcode plus the operands? So for example, if you have like a add instructions, you'll also need some operands with it, right? An X and a Y in this case. Lastly, execute instructions. Okay. So I think this is like the whole normal fetch, decode, and execute cycle for a CPU. And I've already like pre-written the prompt right here. Basically, I was saying I was thinking about implementing a run method inside the CPU class. A run method can probably do the following: fetch the data pointed by the PC, decode the instruction, increment the PC, and execute the instruction. But I do have outstanding questions. Does step 3, where we increment the PC, come before or after step 4, which is executing the instruction? What are your thoughts? And then 2 is, does it make sense to utilize the opcode's JSON file for interpreting the data pointed by the PC? I think it does, right? How do we go about fetching operands? Basically, fetching operands, like additional subsequent bytes from like our initial opcode being fetched from step 1. So how do we do that, right? Do we do that right away, or do we rely on the opcodes.json to do that, like the information in here to figure out? Just want to get its thoughts, right? So I'll copy and paste that into the conversation, and I'll collapse this. Now I hope all this will still work, because we have already eaten up a lot of context for whatever reason, most probably all the code that we have. Yeah. So let's see what we get back from our Qwen 3 model running on our DGX Spark today. And let's just start writing the scaffolding for the run method. So we're gonna be implementing it in our GB CPU class here. We've already implemented basic things like getting data from registers, and also setting data into registers. So I think it makes most sense to have like a def run, and then just do stuff in here. So again, key here is to kind of just pseudocode and scaffold so that we can let the LLM fill in the rest. So what we want is we want to fetch the opcode from PC, and taking a look at the opcodes right here, based off of whatever opcode we have, we know how many bytes to increment. And that's like the step 3 that I was thinking about here. It's like, do we just use these things, right? And then operands here, it's going to be using, for example, for this LD, this is a 3-byte instruction. I'm guessing this is 1 byte. This is another byte. Maybe this is, or yeah, it's weird. And then this one's like 2 bytes. But maybe it's because this opcode here, 0x1, corresponds to, okay, by default, we know that LD, for at least the LD that corresponds to 0x1 is going to always use a BC register as the operand. And then the next 2 bytes off from this LD is going to be a 16-bit number that we can use for adding or loading. So we're going to load this number most likely into this register. Maybe that's what it means. This also affects the following flags. Okay, that makes sense. Did the result end up being 0, negative? I forgot what H meant. And carry. Was there a carry? Well, this is probably half carry. Yeah. I'm not sure. Yeah, I think blank means that it doesn't, nothing happens. Seems like. And then these mean that something actually happened. So this one's probably like the result of 0 or whatever. And then yeah, let's just figure it out as we go along. So fetch the opcode from PC. Then we're going to take that opcode and map it back to opcodes.json file. And then once we've done that, that's basically our decode, right? So this is like the decode step. Then we're going to execute. Then we're going to increment PC by some number of bytes. So this is the order I'm kind of not clear on, but let's take a look here. So looking at your questions about the CPU execution flow and opcode handling. Regarding PC increment timing, the PC should be incremented after fetching the instruction, but before executing it. So we got the right order. So it'll be actually incrementing. Okay. And the number of bytes gathered from looking at opcodes.json. That's what it's going to be. Then what we do here is we're going to execute the instruction. Okay, so that's clear now. That's been answered by the LLM. Okay. So the reason why we do this is because first we fetch the opcode from memory at the current PC value, and then we increment PC by the number of bytes the instruction takes, which is 1, 2, or 3 bytes. Finally, we execute the instruction. This matches the typical CPU execution cycle and ensures proper sequential execution. So this is about right. Okay. I just realized too that we do need to also handle incrementing total cycles. So we also increment total cycles performed. And I think our CPU needs to have that too. So let's add self dot current cycles as a variable. Okay, so every single operation takes some number of cycles. Don't know why it's an array. I forgot the reason why, but let's look at our documentation here. Yeah, I don't think we detailed it. But yeah, we were supposed to implement opcode handlers. So every individual like opcode has its own function or method to execute. Okay, and then this will be like this the kind of like the gist. So it's like one infinite loop, right? Just reviewing. Okay, so regarding the use of opcodes.json, yes, absolutely. The opcodes.json file is perfect for interpreting instructions. Here's how to approach it. Parse the opcode from memory at PC, which is what we're doing here now, right here. Use the opcode to look up the instruction definition in the JSON. Extract the number of bytes, operands, and cycles. Fetch any additional operands from memory. Okay. So we need to know the number of bytes, the operands and the cycles. Based off of this number of bytes, we're going to fetch those bytes from memory. Okay. And then execute the instruction logic. And then we update the PC based off of the instruction length. Okay. Handle flags as specified in the JSON. So increment total cycles performed. And then handle the flags as specified corresponding to opcode. Okay, Now for operand fetching, you will need to, okay, so here we go. For instructions with immediate values, basically whether or not it's a 8-bit and 8, right? Immediate instruction or immediate value, meaning that it's just a number, doesn't correspond to a memory address, this 8 bits here, or a 16-bit number where it doesn't correspond to a 16-bit memory address, rather it corresponds to a 16-bit like straight up number. We're going to fetch next bytes from memory. Okay, so that's fine. How about instructions with addresses, either an A16 or A8, basically a 16-bit address or 8-bit address. We're just going to fetch the address bytes from memory, so either 1 byte or 2 bytes. So for register operands, use the register name to access the appropriate register values. Okay, so the JSON provides all the information needed to properly decode and execute an instruction. Let me say that again. The JSON provides all the information needed to properly decode and execute each instruction. I'll need to toggle ACML to implement this properly. No, not yet. Okay, so far, what's our context? Okay, 151 out of 262. Wow, this is big stuff. Okay, so let's do this. First, what we need to do is this here, this JSON file is going to be a very important file that we need to be able to read from disk and access, right? So you have unprefixed, again, unprefixed and CB prefixed instructions where these instructions, like if we're going into memory, again, like just to review, like going into memory, we have like a series of bytes, right? So we have like 0x01, 0x0c, and then we see 0x0b, and then 0x04, 0x, I don't know, 5, 2, and then maybe this changes to, oops, this changes to CB. Okay, so these are individual instructions, right? But when we hit this instruction here, we know that we're going to have a CB prefix instruction. These two combined right here is going to form the real instruction to execute. Okay, so that gives it, okay, so like unprefixed is 1 byte, right? Okay, and then CB prefixed is actually 1 byte too. The reason why it's 1 byte, even though the length is 2 bytes here, is this is just useless. It's like a signal. It's like a flag to tell us that anything here, we don't look it up as an unprefix, but we look it up as a prefix. So we have 1 byte. That's basically 256 plus 256 different instructions. We have 512 total instructions possible for the Game Boy in this case. Okay, so now, we want to be able to kind of load this JSON into memory so that we can use it to reference. So I think that's like the first code we need to implement is self.opcodes data or DB. Okay, and that's going to be an empty JSON, an empty dictionary in this case. And we can do with open. Okay, let's do, the file name is called what? In this case, let's move this down to source, okay, into CPU as like a supplemental file. So we can just specify opcodes.json in this case here. So opcodes.json, we're going to read as file, and we want to convert self.opcodes. We're convert this to a dictionary so we can assign it to self.opcodes DB. So we're going to use the JSON library. So import JSON and JSON.load F. That's basically the file. We're going to load that into opcodes DB, so that gives us the dictionary. So now we can just access all of this stuff. Now this file path may have to be absolute, relative, whatever, we'll figure it out. But that's the gist. And so for here, this one, we're going to write some pseudocode here. It's an infinite loop. So while true, we're going to fetch the opcode from PC. So let's have like pseudocode to fetch. So def, maybe def fetch, and then that will return something. Okay. So fetch the current opcode from memory based off of PC. So we can have the AI implement this. So just add this and say, okay, well, can you implement this? And let's change it to act. So that does it. So it's going to check the current file structure, and then what is it? Why is it trying to read out codes.json? That's strange. Oh, because I think I have it open, so it wants to read everything that's open, most likely. But that's going to blow up my context again, I think. We'll see. So yeah, I think because the opcodes.json file is such a huge file, I'm leaning towards having it ignore that going forward, since it's just like parsing all of this at the same time. I wonder if we can actually set this so that it ignores that. Let's see. We could probably add to our get ignore. Let's probably try to do that. In this case here, I would even say that we could probably, yeah, let's just add it to our get ignore anything that is like opcodes JSON, and then we could probably move it to the root opcodes.json, and we'll move that to the root, and hopefully it'll get ignored in future and it doesn't blow up our context. So in this case here, I'm just going to ignore all this now, and I'm going to have it resume. And hopefully it's not going to want to read the opcodes.json. Or should I? Let's do this. How do we do this? How do we do this? I want to reset maybe here. Yeah, you know what? Restore. So restore task. Okay, restore files and tasks. Let's do that. Oh no. We should probably add this to our get ignore. Okay, so that's what restore files does. Doesn't seem to be okay. So then this also messed up. So lesson learned. Restore files and tasks is pretty destructive. Okay, so let's do def fetch pass, but we want to basically given memory and PC register fetch current opcode information from self dots opcodes data. I think opcodes db, which is this one. Okay. Sure. Actually, I would even say just fetch current opcode, and I will handle the opcodes db. And yeah, okay. So let's do that. Let's instead of this one here, let's actually send it this and say implement this for me. Okay, now hopefully that it now has an easier time processing context. So in this case here, it looks like it isn't. This is just too big now. So I'm going to offline start a new task. So what I'm going to do now is I'm going to go offline, start a new task, this time without the opcodes JSON, and just give it like context. as like, okay, opcodes.json. Don't read it. It's huge. Is for storing all our information about opcodes, right? So I have a duplicate right here, so I'm going to delete that. Okay. So in this case, let me just cancel and let's just start over and hope for the best. So I'll do that. I'll do that off camera. Okay, so now let's have it implement this again. Try to implement this. Okay. Let's see. Okay, great. It's working faster. Okay. I hope it doesn't change too much again. It always makes me nervous when these local agents try to do stuff because it does way more than it needs to do. Yeah, it definitely. Okay, that's a helper. Okay. Okay. This is save and see what it does. Okay, so it fetched the byte. That's fair. It just basically gets the one single value in memory for in a memory address using our API get memory. And then oh, it's this thing again. Please just calm down. Let's only implement what I ask for. Okay, so let's just cancel that, send that. In this case here, we fetch a byte, which is only one value from this address. When we want to fetch a word, that's just basically 16-bit. So we fetch the low byte first because little endian, right? So little endian system. It's low then high. So then we also get the high byte, and then we return back the word. Okay. And so what's going on here? Okay, that's okay. Then so we return the word and return the byte, right? These are values still at a specific address. Now, in this fetch here, this is like normal fetch. We want to fetch one byte. Okay. Save. That's why I don't like AI that acts, right? Like it just keeps going on and on and on, even though I don't want it to. And I think that's like the difference between like decline in general versus something like cursor. And my take here is that if I keep having issues like this, I would probably not use local coding agents anymore. Simply, it's not like local models suck or anything. It's just like the ecosystem around it is just not a good experience, right? Like there's a lot of configuration going on, and it's really dependent on your own infrastructure. Fine for like really light work, but I just feel like it holds like you want a good experience. You want to just code and not have to like fiddle around. And so far, for me, I've fiddled around. I want to be able to move from computer to computer and just be able to work in the same repo really quickly. And this is not really providing me that type of experience right now. Maybe I need to just learn how to do things better. But my assessment so far is that these things are doing way too much. I think but that's an agent, right? It's supposed to like generate a bunch of code for you. I don't know why it's even creating a demonstration. I was not even interested in that. So let's just see, right? So it didn't even like code the demo script correctly. This how it's like missing the code to run as a main method. It still didn't even do that too. It's probably gonna be in this loop. Yeah, so it's pivoting just like, okay, well, let's just do a simple test. I was so eager. It looks like I can't pull it off anyway. There you go. In this case, I think this is just, yeah, it's a good idea to just remove this. It's not very useful. But the test fetch is good. I like the test fetch. Let's see what type of tests it did. It creates a CPU class, and then it just sets some values in memory. Then it fetches that value at that location. It should be AB. That's fine. That's kind of like a memory setting thing, right? So fetch word should be, what is it? EFCD, right? Because we fetched the low first, we fetched the high, and then we merged the two, so it's EFCD at this, starting at this memory address right there. So that's cool. Yeah, and then fetch opcode here. Basically, again, we set the value as 0x01, which is the load BC with a 16-bit immediate. The PC starts out at 0x0. We fetch, and then we assert that the opcode fetched at this memory address is 0x1, and then PC should have been incremented by one single byte. Interesting, because if we look at the opcode LD, right, LD is on prefix 0x01, bytes is 3. Okay, so let's probe a bit here. Let's probe a bit. You said that in this test, PC is incremented by 1, but should it have been incremented by 3, given that the opcode 0x01 corresponds to an LD instruction followed by a 16-bit immediate? Is that true? I don't know. That it doesn't like throw everything into context. That's like my concern with that opcode's JSON. It's huge, and I expect at least these models to recognize that and run the right MCP tools. Maybe I don't. Oh, it's probably because I don't have it, but there should be some built-in ones, right? So I also have Cursor installed too, so we might just move to that. I mean, at the end of the day, we're not restricting ourselves totally to local AI. That was just the goal. We're just creating an emulator right now so that we can just mess around with having an AI control it. Reason why I decided to do that from scratch is because, first of all, it's fun to just create some projects with AI. But also, I think we can always modify it to our liking, so it gives that flexibility. So I'm at this point, I'm kind of annoyed that I'm having a hard time. Again, I don't know, skill issue or anything like that, but I'm having a hard time just kind of bending the AI to what I expect it to do. And so maybe I might just like pivot right now while I still have some time to code. So let's see. Yeah, so let's do this. Let's have it fix this and review the rest of the code right now, and then we'll clean up, and then we'll move on to maybe Cursor. Or actually, we could do Copilot here too. Who knows? Yeah, let's just try Copilot while we're here. Let's see here. Let's just review this code here. Fetch byte. We fetch a single byte from memory. We fetch word. Okay, that's logic is correct. We fetch the current opcode from memory. Add that PC and increment the PC. Okay. That's correct. But then we run one CPU instruction cycle. So in this case, opcode is going to be self.fetch. Check if it's a prefixed opcode. Basically, check if it's 0xCB. And if that's the case, then we want to shift that 8 bits so it becomes 0xCB and then XX. Whereas the next XX corresponds to that next byte. Then we had to increment again, right? One more time. Fetch had already incremented it once already. Then we had to look up the opcodes in our database. And in this case here, opcode info is going to be set to none. We're going to try and get that object from unprefixed, right? That's interesting. Let's see here. Okay, well, sure. So we're gonna either get it from unprefixed or prefixed, CB prefixed. Now, here, I guess that makes sense because opcode has been shifted with CB, and if we look at the CB prefix, I think it might have the CB in front of it, maybe. No. So that code might be wrong too, actually. I wouldn't even use this as like logic. Okay, I would actually rewrite this a little bit to be clear. Let's do that afterwards. And then if we don't have any opcode info, then yeah, that's going to be error. This is going to be so this AI is going to now correct the test file. Okay, so there should be incrementing by 3 total. But I guess looking at this, it was kind of right before, because now that we read the code, that fetch should have only incremented 1 anyway. And this it didn't really mean to fetch all the bytes, but technically when you fetch, right, you're fetching all the bytes in this case. So yeah. Okay, so let's save, and then we'll just review the code later. Wowza, what is this? Okay. Let me fix the test file properly. Yes, give it a chance. Okay, save. It still probably has no idea what's doing wrong. So let me just run the test and make sure everything runs correctly. Well, you don't have a main, so that's the problem, right? You don't have a here. It's missing this piece of code. Oh. It's missing. If you take a look at this, it's missing this thing. You're gonna test.main. It probably doesn't realize that. Yeah, apologize for the slow start again. But hey, I want to show you the struggle. I mean, I think a lot of people claim that they're coding with local AI, but I don't know. I'm a little skeptical whether or not that's actually the case here. I think a lot of people are probably using open source models, yeah, through like some open source service, but right on their physical machines, I'm quite skeptical now. So I don't think we're there yet, to be honest. See, it's like this struggle here is just constantly happening. So what I'm going to do is I'm just going to forget this. I'm going to cancel. Here, we're just going to fix it ourselves. So I am going to enable Copilot. I'm going to enable Copilot. And then we'll see how it goes. So I'm going to disable client, because I don't want so many things running. And then I will have, I'm going to restart after, yeah, let's just restart. Now I have Copilot. And then let's see if, I'm just going to trash this. We're back to a good spot, I think. I don't know what this API is here for. Let's just delete it. It's silly. Okay. So, okay. Yeah, let's get it up to speed again. Okay. So what I'm going to do is I'm going to, I don't know why it's like this. Okay. Let's do this. Okay. I am going to pass this in, and I'm going to run with all the prompts again. The model I am going to be using after I've logged in with GitHub, excuse me. So I'm going to be using Claude Sonnet 4.5, and I'm expecting this to be much better. Okay, it's not a cursor, but hey, I think anything is going to be a huge upgrade now. So yeah, let's change this to be just at DesignMD. So how we do it? Plus, how do we do this? DesignMD. I think I'll know how to search this up. It's smart enough. Okay, and then I'm going to even do this. instead of ignoring opcodes.json, I'm going to leave it there and see how I can handle it. Let's see how good it is. Okay. Now, okay. So design.md is included in this case. And let's shoot it off. Should we do agent or should we plan? Let's just do plan. Okay. So let's get it up to speed and then go from there. So already it knows that it shouldn't be reading opcodes.json incomplete. It should just read the first 100 lines. So already Claude is smarter. And it's much faster already. So that's okay. Yeah, so it finds some incomplete things here too. But that's okay. Okay, so let's just continue on. Don't be too eager on things. I will drive the process. You serve as my sounding board and rubber duck, and will assist with implementing scaffolded code as necessary. Okay. So I like giving ground rules because of that. Okay. Okay. So first of all, this one should actually be infinite loop, I think. But we could say max cycles, right? So let's do max cycles equals -1. Okay. Meaning that it'll be infinite, right? So so we could go while true. Okay. If current cycles, right? If self dot current cycles in this case, and I'm thinking it is up here. Yep. If self dot current cycles is equals to max cycles, then we want to break. Okay. Otherwise, I need to turn this off. How do I turn off the inline? Disable completions, hopefully. Okay. So now, if we're at the max cycles, we'll break. Otherwise, we'll just continue running things. So how to continue running things? Well, basically, one CPU cycle. So we'll fetch, and then we'll check to see if it's a prefixed opcode. And then what we want to do is we want to look up the opcode in the database. Here is where it gets interesting, right? Well, instead of checking if it's unprefixed or CB prefixed, we'll check the opcode instead. So if opcode is equals to 0xCB, we want to fetch the opcode info from self.opcodesDB, CB prefixed. Okay. And then at the opcode here, basically F0x opcode 02x, like that. That will turn it into that hex string. Else, we're going to try and fetch the opcode info from the unprefixed. So same thing, unprefixed. So I think this is actually a better implementation than what the other model tried to do. So I don't know whether or not we're truly off to a good start with this newer way of doing things, but I feel positive. Okay, so now we've fixed this issue, right? So this fetches the opcode. What we want to do here is we want to have Claude just review the part where we just fetch the opcode, and we will then increment, right? Increment the number of bytes total. So right now we're just checking to see if we're doing this correctly. So yeah. So here we can, I think it's going to be Control Shift. How do we add this inline? Let's see. Let's figure it out. So how do we add this inline? Add selection to chat. Do we always have to right click on it? Guess so. Okay, add selection to chat. Oh, it already does automatically. Okay, well, Can you review this piece of code? Okay, I just want to make sure I am at least fetching a single opcode correctly. Operands, execution, etc. come later. Let's just work a little at a time. Okay, so it's gonna review that piece of code for me, just to make sure I get it right, because I've only written one type of emulator in my life. So let's see here. So it reviewed, and so it just has some opinions. So let's just read the opinions. Basically double checking for 0xCB, so it's true, I did that. Okay. So the opcode is no longer equal to 0xCB, which is true. It's actually 0xCB something something something, right? Okay, so dictionary key format. When the opcode becomes something like 0xCB40, okay, it's funny how I used that same example earlier. Your format string is this. Okay, so that's wrong. But I need to check your opcodes.json because keys are stored as 0x40 or 0xCB40. Okay, so opcodes.json does indeed store them like this. Okay. Now, here's the fix. So basically, we want to check to see if it's prefixed. That's fine. We don't want to merge yet. So this is not necessary, right? So in this case, we can get rid of this. Okay, this is going to be actually the real opcode. Okay, and then what we can do is we can keep this here up here, and then merge that into this branch. Take this away, and then I think this looks much better. Let's see. So similar to these, I guess, but let's just ask, is this better? So ask the following. Okay. Is this better now? Okay, so yes, much better. So it's a more correct logical flow. I like it like this because it's just easier for me to read. But yeah, if opcode info is none, all right, the check at the end may not catch missing opcodes. If the key doesn't exist in the dictionary, you'll get a key error instead of none. Okay, so maybe we should use get instead. So let's just use get right here. That's a better, I guess, idiom. Is that what we call it? So get here. Okay. And then we'll have, let's say, get here. Alrighty. And then, yeah, if opcode is none, we raise a not implemented error. Okay. So now what we want to do is in this test here, we want to test fetch opcode. Let's just blow all this away. Okay. And save it. And then let's have it implement basic fetching. Okay. So can you write some tests here that has the same coding style as the tests found in @tests? I don't know how to even like attach context. How do I attach context? How do I attach context to this thing? Let's see. How do I feel so silly. Is it @ is it slash @ is it slash? Okay, how do I do this? Okay, let's look. How to attach context in GitHub Copilot Visual Studio. Okay, so how do we do it? Plus pound. Okay. Okay. CPU, test CPU. Okay. In fact, no, let's do this. Found in pound tests. Okay. Remember, our CPU implementation for fetching so far is only concerned with fetching the right opcode. Okay. And the opcode info. Can you write tests that minimally test this? Our run method is in an infinite loop, but I think passing in the appropriate max cycles will make it not be. Okay, so let's have it agent mode, and then let's just include that and let it go. Okay. So test fetch stop high. I expect it to be smart enough to know that it needs to do stuff in here. And it's going to get familiar with opcodes JSON. And then let's see. What's it going to come up with? Now that is some fast code generation right there. Okay, sure. That's a lot, but let's do it. Okay, so there's one. Okay, let's just read it. So I've written tests that match a coding style for existing tests, and I'll just keep it. Okay. The test covers basic fetching, fetch byte, fetch word, opcode fetching, both unprefixed and CB prefix code, single instruction execution using max cycles 1 to test the run loop, multiple instructions testing that the loop correctly handles multiple cycles, mixed opcodes verifying the CB prefixed 2 byte and unprefixed 1 byte opcodes advance the PC correctly. Note there's one issue in your current run method. Self current cycle is never incremented, so the loop will never exit. That's true. Okay, so let's do it. So in the loop body, we want to just basically do self dot current cycles plus equals 1. Okay. Here, I fixed it. Okay. So that's good. Now let's run our test. Okay. Yeah. Run the fetch tests now. Okay, so let's have it run those tests as an agent. And tell me. So Python m unit test.cpu test fetch allow run. Okay. Python is not. We need Python 3. Silly. Okay. Good. A test pass. Now let's see what kind of test it actually wrote. Okay. So here, it's gonna be basic so far. We create a CPU, we test fetch one single byte. Again, this is very familiar. This is like what Quen just did, so I have a feeling that they train on the same type of thing. EFCD, okay, or maybe it's like what we had before. I don't know. So test fetch unprefixed opcode. This is not the CB one, so this is the no op one. So you set in memory at this address the no op opcode, and you're gonna set the PC here. You're gonna fetch that there. You're gonna make sure it increments by 1. That's correct. Okay. So you're gonna fetch unprefixed opcode with operands. So basically LDBCD16. So you're gonna have 1, 12, and 34. So this is going to be 3412 is going to be the value, the 16-bit value that's gonna be loaded into BC. So CPU registers PC is gonna be 0x0000. We're gonna fetch. So we're gonna assert that okay, the opcode we fetched is 1. That's correct. And then PC should have been incremented by 1 just for the opcode fetch because we haven't handled the operand fetches just yet. So that's correct. Okay. Test run single unprefixed opcode. Okay, so unprefixed single opcode. Again, a no op. This feels, I guess, repetitive. So let's ask this. Okay. Let's add selection chat. This feels repetitive. Don't we already have this? Okay. So CB prefix, that's fair. We have CB00. This is also, I feel like this is also repetitive too. Okay, what was it? Test, fetch, and prefix operator already test the basic fetch mechanisms that we already saw earlier in 23 to 31, which is up here, which is why I remember it's right here, right? However, is testing the full run loop, which includes fetching plus the opcode lookup logic, so it's slightly different scope. Okay, sure. Why would that be a slightly different scope? I mean, I'm failing to see why. Can we just consolidate? Can we just consolidate all of the where's it? Consolidate all of the redundant tests. Okay, so hopefully it goes really fast, right? Okay, so delete a lot of code. That's concerning, but sure. So I think that's what Gwen did better at. It was able to just create the only like the tests necessary. So this looks better, right? Like mixed op codes, whatever. Run for 3 cycles. Okay, we should have incremented our PC to whatever. By 4 it looks like. So no op CB prefix. It's 2, 3, 4. Fair. Okay. We should have ran for 3 cycles. Not sure if that's correct, but that's because of this, right? Let's ask. So actually let's run the test again. Okay, let's rename. Okay. Let's rename test fetch to be test fetch opcodes only.py. So let's rename that. And then what we want to do is we want to have it run the test again. So we'll just allow. Okay. So now run the tests again. Then we're going to run the test again. And then we're going to ask it, well, does it really make sense to only increment the cycles by 1? Okay. Okay, perfect. Looking at this, right? Looking at this line here, does it really make sense to only increment cycles by 1? Given that each opcode info has a specific number of cycles executed. I know we haven't implemented fetching additional data yet, but I want to get your thoughts here. Okay, so right now we're just fetching opcodes, but at the same time, really, if you think about it, those opcodes, if it's like consecutive, it's not like one after another, right? There's gaps because of operands in between in memory. So I love how it made stuff up saying that, oh, well, current cycles is how many instructions, but really I want CPU cycles. Current cycles is really counting instructions, not CPU cycles. I want option B to get the actual cycle count. This is what I want, really. Use the actual cycle count. Okay. Now, I have fuzzy memory. Okay. I think it makes sense to actually increment by the real cycle count. But my memory is fuzzy. Why is it that in opcode info, the number of cycles is in an array? What does that mean? Can we update design.md to explain the structure of opcodes.json? Okay. I think that's actually useful information to have, right? Yeah, variable number of cycles, okay? Depending on that condition. Say, for example, let's take like that JRNZ. R8. So conditional jump might take 12 cycles if the jump is taken, 8 cycles if not. So if not taken, 8. If taken, 12. Okay. For instructions with fixed timing like no op, the array just has one element. So want me to add a section design.md explaining the opcodes JSON structure. Please do update the design.md. So like I noticed that like we're flying much faster now, right? Like because we're using a cloud model in a sense. I don't know whether or not it's just because this interface is better, right, with Copilot in that it does things the right way where it doesn't try to load the entire opcodes.json into context. It just reads portions of it at the time. Not sure whether or not it's just because Copilot is just built to be more integrated with VS Code. Not sure what it really is. Or it just could be just the fact of the matter is that Claude Sonnet is just that much better. It's a huge model. So anyway, design.md, I'm going to keep that and I'm going to read this here. So opcodes JSON file contains metadata for all CPU instructions organized into 2 top-level objects, unprefix and CB prefix. Each opcode entry is keyed by its hex value and contains the following fields: mnemonic, so basically the assembly instruction; bytes, the total instruction size bytes; the cycles, number of cycles consumed, okay, and then it has that explanation right there. And then operands, the array of objects, basically the list of operands for the instruction. Each operand has a name, either a register or value name. Optional bytes, which is size. Okay, so let's take a look at opcodes.json again. Let's take a look at unprefixed, right? So the unprefixed with LD, we see that 3 bytes, 12 cycles, and then you have the operands right here. Okay, so this is 2 bytes for this one here. This one is just the register name. Okay. Sure. Immediate, whether it's a direct value versus memory reference. We'll come back to that later. And then flags, how each instruction affects CPU flags, Z and H or C. Values with a dash means unaffected. 0 means reset to 0. 1 set to 1, or the flag letter. Okay, if the flag is set based on the operation result. Okay, so Z means, well, if it's 0, then you'll set it to 1. If it's not, it'll set it to 0. And then there's specific instructions that kind of hard coded to 0 or 1, no matter what, right? Okay, so here's an example: fixed cycle instruction. I love how it uses an op, but it's fine. Conditional instruction, variable cycles. Okay, this makes more sense. And then that's about it. So I like this. I'm gonna commit that right away. I'm gonna commit this, and I'm gonna commit this here, and I'm going to commit, well, let's not commit that yet. So let's edit this GB CPU to be more correct. So opcode info is going to be cycles. And then let's just assume taking the first one. So for now, assume the first number of cycles for now. Okay, this could be collapsed. Okay, so now let's ask, okay, I have made the change, but do we need to update tests, right? So I have made the change, but do we need to update tests? So let's have it decide that. Let it be the judge. We need to update the tests. Yes. Want me to update the tests with the correct cycle counts? Yes, please do. Okay. Now, is it going to find the right test file to update? Let's see. It did. So this is a much better experience already. Okay, now it's going to run the test again. And let's see if it ends up passing, which it does. So that's great. Okay, cool. Let's see what it did here. It did find, okay, so it did correct the max cycles because it needs to know that it needs to run more now because we're incrementing a lot more than before. So we'll keep that here. We'll check that in, and then we'll also check all this in. Okay, great. So let's just add this as basic fetching. And we'll git push. So now since we have something that basically fetches one opcode and should be the appropriate opcode, whether it be normal opcode, normal opcode or CB opcode. We're able to get that information now into opcode info, and just like for a reminder, the opcode info is an object that looks something like this. We'll know the mnemonic, but what we need to now get are the operands, if possible, right? So let's have a discussion here where we can think about what we need to do. So in this case, how do we relate the bytes, cycles, and operands together? Never mind about the flags just yet, because we're not executing. We're just still in the interest of like fetching. Because we've only fetched, at this point, only the opcode. We need to be able to fetch the operands. Okay? So, given this example here, if we have fetched our opcode that one single byte, assuming it's an unprefixed one, we still need to be able to fetch, in this case, 2 more bytes. And that's actually N16. Correct? I'm thinking here is that, well, if we know the opcode, we'll assume that once we fetch it, we take a look at what the number of bytes are here, the belonging to that opcode. In this case, it's 3. We just subtract 1 byte from it because we know that an opcode is a single byte. And then based off of that result, we can fetch the number of bytes after the fact. And that will help us determine, I guess, the operands that we need to parse. In this case, if let's say this opcode is 3 bytes, we fetch 1, we have 2 bytes left. Based off the operands here, we'll have N16, where it's 2 bytes. So we'll dedicate the rest of the 2 bytes to be an immediate 16-bit number. I'm just thinking on the fly, but this sort of makes sense to me. Let's just try another example here. So maybe if I scroll down to something that is substantial. Let's see. I could just probably search for it too. Bytes. Maybe 4. Is there a 4 one? Is there a 3? Okay. Well, there's a JP one. Okay, we could take a look at that. Maybe not. Let's take a look at more JP. How about call? This one's interesting. JP call. Okay, whatever. Call. So call itself is 1 byte. So that leaves us with 2 bytes left. And the operands here happen to be just one 16-bit number that represents an address. So that's 2 bytes itself. So we can just now subtract 1 byte from the 3 bytes total, then subtract 2 more bytes, and then we know that we fetched everything when we have 0 bytes left. So that's like the gist. And I think I should probably express that. This way we can probably feed that to the LLM because we're trying to work with it. So given an instruction, for example, fetch the opcode. So that's normal. That's what we did last time. Opcode leads to opcode info. Okay. And then opcode info has dot bytes, and that is an integer. Okay, so let's call that num bytes. Now our opcode is already 1 byte in this case. Now we have a 1 byte opcode, then that means rest is going to be num bytes minus opcode. Oops, minus 1. Considering this one here, like taking that into consideration. Now, how we determine like how to go and fetch the rest of those numbers is based off of operands, right? So now we look at opcode info dot operands, and that is actually an array. Okay, it's a list. Okay, it's a list, and for each of those operands, for each operand, what we have now is bytes inside those objects. So an operand dot bytes. So we're going to do that repeatedly. So num bytes minus operand dot bytes. And then if basically stop this loop when num bytes is 0. Okay. That's my training data. It's like a high level overview in how we can determine how much to fetch. And so let's try to turn that into text and then see if that sounds like I guess like sound logic for us to try to implement. So in this case, let's just draft our prompt in a text editor and go from there. So now, so I'm going to think, and I'm going to think out loud. So it's going to sound pretty bad, but I think once we type it, it'll sound smooth. So right now, we are only fetching 1 byte at a time. This is the opcode. However, at the end of the fetch, in what we have currently, do we have word wrap? What we have, currently implemented, we are actually incrementing the number. We are actually incrementing the PC by the total number of bytes of that specific instruction. Given that we did this, we still need to actually fetch the rest of the bytes in between. Here is what I am thinking in how we can do this. First, opcode info has a property called bytes. This is the total number of bytes that a specific instruction corresponding to that opcode needs. So for example, LD, which is 0x01, okay, that instruction needs 3 bytes. If we have fetched the LD opcode, that leaves us with 2 bytes remaining to fetch. Okay, and then basically we could say let's reference opcode info.bytes as num bytes for simplification. So, okay, we have 2 bytes remaining. That leaves us with num bytes equals 2 bytes remaining to be fetched. Now, I am thinking that what we can do to parse this out is to look into opcode info.operands, which is an array of operand objects, and inspect to see if operand.bytes exists. If so, we can just fetch those number of bytes and then increment and decrement the num bytes until it is 0. We do stuff with the bytes, with the operand info once fetched, but right now only concerned with getting the PC and fetching correct. So what do you think? Is this sound logic? Does this translate well to 0xCB type prefixed instructions too? Okay, so I'm going to send that to the LLM just so that the LLM and I can understand each other. In this case, I would say let's add was it pound? Let's add GP CPU to the context. Let's also add opcodes.json to the context. And then I would like to remove this, but I don't know how. Okay, that's okay. Maybe if I don't select it. Okay, great. Okay, so now let's paste all that in and then see what happens. See what Claude says. Okay. So Claude thinks that my logic is sound for tracking how many bytes to fetch. Let me walk through it. And here it cleans it up better than me. It's probably going to explain it way better than me. AI, you know. Okay, so for unprefixed instructions, so opcode 0x01, which corresponds to a load, basically 16-bit immediate value into the register BC. We basically fetch 1 byte, gives us 2 bytes remaining, 1 byte being the opcode. Then we want to sift through the operands and then basically start subtracting the number of bytes. Since operand 1 is BC with no bytes field, it's a register. We just have 2 bytes remaining. Operand 2 is going to be an N16. I don't know why it says D16, N16, but whatever. N16 will fetch 2 bytes, and then we'll have 0 bytes remaining. That leaves us with nothing. Now, for CB prefixed instructions, looking at the JSON, CB prefixed opcodes have bytes 2. Is that true? Let's look at it. Okay, so let's look at a very simple one. Let's collapse unprefixed. Okay, here we go. So bytes 2. Okay, so yeah, it's true. So bytes 2, which includes the 0xCB prefix and the actual opcode. So for CB instructions, after fetching both the prefix and the opcode, you've already consumed all the bytes. Okay, most CB instructions operate on registers directly with no additional operands. Oh, that's good to know. That's good to know. Most of them do. So that's okay, right? Like we've already incremented the PC like once when we fetch CB, and then when we fetch it again, do we do that? Yes, we do. So we fetch once to increment. That turns out to be a CB. Then we fetch again, and then we actually increment the PC again. So that's okay. Well, what's the potential issue here? Right now, you're incrementing PC in fetch and then again manually for CB prefix. You need to be careful not to double increment. Okay. Suggested approach. So after you look up the opcode info, bytes remaining is going to be, okay, -1. That's our logic. For CB prefix, we've already fetched 2 bytes. So we have to negative, okay, so -1. Then we fetch the rest of the number of bytes. Well, yeah, this is exactly it. Yeah, this is it. Okay, no, that's fair. I think this is just like a warning. It's like, hey, you just got to remember that you know, you've already fetched 2 bytes, so you gotta take into consideration of the math as appropriate. So, yes, this is exactly it. Yes, yes, this is my thought. Okay. Um, okay, so I think let's try to integrate that. Um, I'll start us off, us being me and Claude, and maybe you too if you're following along. So I'll start us off with scaffolding, and then I'll have the LLM fill out the rest. So here's the plan and how we should work together going forward. We plan together and discuss. I come up with scaffolding. You fill in the rest of the implementation when I tell you to. Okay, so that's like ground rules for me and the LLM going forward. And it sticks with that for pretty much the rest of the conversation. Okay. Now, what I want to do is I want to just adapt this into this fetch here. So we've already incremented PC once when we call fetch, and then if it's a CB prefixed instruction, given the opcode info, at this point, we're guaranteed that opcode info has something, right? We can here just increment PC as appropriate per operand. Okay. Now in this case here, what we want to do is we want to define the num bytes remaining. So let's say num bytes is going to be opcode info, and then let's say let's have a flag that says is a prefixed instruction, is prefixed opcode. It's going to be false. And then if let's say opcode is 0xCB, we say is prefixed opcode equals true. So that's like a flag here. So what we want to do here is opcode info bytes, okay, is going to be subtracted by is prefixed opcode. That is going to be well, 2 if, right, is prefixed opcode, else 1. Okay. Now, while num bytes is greater than 0, what we want to do is go through all the operands and then just check to see if there is a bytes key inside that object. So let's save the object here. So operands is going to be opcode info operands. Okay. And then let's check for every operand. So maybe a for loop would have been better here. Yeah, let's do a for loop. Maybe there was a point to that. So for operand in operands, okay, what we want to do is we want to check to see if the bytes key is inside operand. Now, if so, we just subtract num bytes. Okay, so minus equals operand num bytes. Operand num bytes, or not bytes, bytes, like that. Then I guess what we can do here is self.pc maybe, self.registers.pc plus equals, I guess operand bytes. Okay. Now, see, I don't even know why I'm doing this num bytes thing, but now I realize that like the whole point was to just increment PCs, right? So in this case, if num bytes is equals to 0, we'll just break. Now let's clean up this logic because there was no point to that. Now that I realize it, and again, I'm just like thinking on the fly and programming on the fly. So if you think about it, this is like this was like totally not necessary. All we had to do was just subtract the num bytes here, right? And then just we didn't even need to do that. So let's do this. Let's go for every operand, and then let's just do this. Okay, if bytes in operand. How's that? Okay. Now, whether or not we care about this, I don't know. We'll deal with it later. Okay. Let's just give Claude a heads up. Heads up, I think this is a more simplified version to just update the PC. Maybe this is all we need for now, and then let's just let's what am I doing? Okay, let's actually save some variables so that we can actually do stuff, right? So we fetched bytes, but they're going to like nowhere land. We're just incrementing the PC, which is like kind of wasteful. What we want to do is we want to repeatedly fetch this thing here, and that's actually what we truly want to do. This will actually increment PC itself, but this was assuming opcode. Maybe this should be called something else. We have a fetch. Oh yeah, we have this fetch byte, fetch word. Okay. Maybe we just use fetch byte and fetch word in this case. So if the number of bytes is, let's say 1, right? We'll just fetch bytes, and then we'll just fetch word if it's 2 in the operands. I don't think we fetch more than that per operand because that's kind of impossible given that the Game Boy is only 16-bit addressable, and it's either a 16-bit immediate or a 16-bit address. If operand, so let's determine something, like let's try to see whether or not we need to fetch like 1 or 2 bytes, right? So we're gonna say num bytes per operand, or let's say for operand is going to be operand bytes. Now, if num bytes for operand is 1, we want to fetch word. So fetch self.fetch, or sorry, fetch byte. And the address here is going to be, in this case, self.registers.pc, whatever's in the PC. Okay? Because if we think about memory, let's say this is memory here. Okay. Let's just say memory. And just these are just values. Let's say 100, 200, 222, 99, 56, 667, 131. Let's say the PC is like right there. PC is pointing to address 0, 1, 2, 3, 4, 5, 6. PC is equals to 2. We want to get the value within address 2 for PC. Now, that's why we call fetch byte at the PC location right here. Else or elif num bytes for operand is 2. We want to fetch the word in this case. Okay, now else, don't know, we can just throw an error right now. So raise value error, not implemented yet. Not implemented yet to fetch more than 2 bytes. Okay, I don't even know if it's possible. So we can just ask, right? So is it ever the case where an operand is more than 2 bytes? Doesn't seem to be, right? Because it's either a 16-bit address or a 16-bit immediate for a single operand. Well, max, I should say max 16-bit, because it could be 8, right? So, yeah, operands are most 2 bytes. You'll see all this. Okay, so let's actually update design.md to mention that. Place it in the appropriate section or create a new section. Make it in same writing style. Okay. Just trying to document as much as possible so that if we end up with let's say using a weaker model later down the line, it has all the context it needs. It could probably be useful to do like, I don't even know if RAG would help. Let's see what it wrote. Okay, operands in Game Boy instruction set are limited to a maximum of 2 bytes due to the 8-bit CPU architecture with a 16-bit address bus. Sounds about right to me. Okay. I think here it's going to be interesting in that, okay, how do we store the operand values themselves, right? Let's not worry about that just yet. Let's just pass on these. Okay. And then so to do, okay, to do, and then let's have Claude review this approach just for, I guess, confidence, since we're doing this for the first time. Okay, so I was thinking if num bytes for operand is 1, we fetch 1 byte where the PC is currently pointing to. And if num bytes is 2, we fetch 2 bytes word. So that makes perfect sense. So you're actually reading the operand data from memory, not just skipping over it, then advancing PC. This way you'll have the operand values available when you implement the actual instruction execution later. That's true. So the flow would be 1 byte operand, okay, read a byte, then PC plus equals 1. Right, that's true right here. And then 2 byte operand, read the word, little endian, then fetch or the increment PC plus equals 2. Right now, you're not storing operand value anywhere yet, since you're not executing instructions, but at least you're reading them from memory to ensure fetch logic is correct. When you implement actual opcodes, you'll use those fetch values. Sound right? Yes, that sounds right. Okay, so now that we're able to increment the PC, why not have Claude update the tests? Yes, sounds right. Can you update the tests fetch or test fetch opcodes? Test fetch, actually not opcodes. Can you create new tests? Can you create new tests in consideration of this piece of the PC advancing correctly? Now use test fetch opcodes only as inspiration. Don't use the same file because that fetches opcodes only, right? I don't know. Maybe that's gonna fail after stream logic. So let's see. Maybe we'll just delete that file too, because I don't see any point anymore. It's like, it's relatively like cheap to just generate new code anyway with an LLM. So created test fetch with operands.py with test to verify if PC advances correctly for one byte operands. Okay, 2-byte operands, and then multiple instructions of various operand sizes, mixed scenarios, no operands, 1-byte, 2-byte, and CB prefix. Okay, so let's see. Let's see what it did. So let's just keep it. Let's just keep that too. Okay, so test fetch with operands. Test run one opcode with 1-byte operands, so should have advanced by 2. That's correct. So we want to assert that PC now points to 2 after going from 0 to 1. Current cycles, that's fine. Okay, so now 2 bytes. We should end up at 3, I guess. Yep. Then this one is multiple opcodes with operands. So we know that most likely 0x06 is it just fetches 1, or yeah. So 1. So that's 2 bytes. Then we have a 3-byte instruction, and then there's a 1-byte instruction, and that should end up with 6. 0, 1, 2, 3, 4, 5, 6, or 0, 1, 2, 3, 4, 5, and then 6 would be where it's currently at. Okay. Yeah, I'm gonna trust that. So let's run it. Let's run this test. So let's run it, see if it passes. And then I'm going to consult Claude again about the other tests, whether or not we still need it. And then we'll go from there. It's easy, right? So now let's think. Do we still need test fetch opcodes only? Do you think it still works? Want to try it? I'm not even tricking the LM. I'm just too lazy to go look and see if things are still working or not. I'm just purely being lazy. So yeah, it still works. Okay, so whether or not, okay, so does it make sense? I don't know. The old tests remain valid because NOP and CB prefix RLCB don't have operands with the bytes field, so your new operand loop just skips over them. Both test files serve different purposes and can coexist. Okay, sounds good to me. So they can coexist. Sounds good to me. I was just concerned if they would be able to coexist or not. Okay. All right, so we're able to fetch things now. Let's, before we move on, let's just kind of ask Claude if there's anything else we need to consider for fetching, or like whether or not Claude also agrees with us that we're ready to start storing operands and possibly writing our own I guess handlers for instructions. Okay. Nice work on the incremental approach. Haha. Okay, so now I think we need to establish whether we are ready to move on away from fetching logic. Do you think we have a generalized implementation and is enough to start thinking about storing the operands and performing execution? So I just want to know whether or not we still need to think more about the fetching part. So let's assess what we have, what's working. We have opcode fetching. That's true. We have PC advancement for opcodes, PC advancements for operands, which is this stuff here. Cycle counting, so stuff right here. And then proper handling of instructions with the operands. What's not implemented yet, actually storing the fetch operand values. You're calling blah 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 into do's but not capturing the return values. Yep, that's true. That was intentional. And in any way to pass operand values to execution handlers. That's also intentional. Okay, so question: when you move to executions, how will handlers access operand data? Interesting. Options: store operands in instance variables like self.current operands that handlers can read, pass operands as parameters when you eventually call handlers, have handlers fetch operands themselves from memory using PC offsets. for a generalized implementation. Let's say you're 90% there. You just need to decide how to bridge fetch operand values, execution handlers. And once you have that design in mind, you're ready to move on. Okay, so I do have a plan. I was actually thinking something like this, keeping the current operands in the list. But I want to make super duper sure that, I can make the assumption that the order is like the order of the operands appearing in memory. So let's just ask that. I was actually thinking the same thing about storing operands in an instance variable where each operand value is an element in some list. I am just wondering if there should be a need for concern about ordering, etc. I would assume that earlier items in list are operand values I grabbed early on, later being last, etc. I don't even know. That doesn't even make sense, but whatever. It should know. It's big enough to know. So then handlers can reference this instance variable. Now, tricky thing is that if we're keeping the operand values inside the instance variable as a list, we're going to have to clear that list every once in a while, right? So that's going to be on every single run. Every single call to run, we should probably reset that list to be empty in this case. So now tricky thing is that we need to remember to clear this list. Would it make sense to just clear the values away on every iteration of run? Let's not worry about the execution handlers just yet. Let's focus on being able to store the operand values in either registers or instance variable. Okay. Yeah, so consider the fact that we can get the operand value, but there are certain instructions that also get that utilize maybe the registers too. So how would that work, right? So great plan. Storing operands in an instance variable list makes sense. Here's my thinking. The order in opcode info operands dictates the fetch order, so your list will naturally be ordered correctly. That's good. We wanted to just confirm that. First operand fetched, index 0, second index 1, etc. Man, these things explain things way better than me. Like, I can't even word my question correctly, but it's like spot on. Okay, so yes, clearing at the start of each run iteration makes perfect sense. You want a clean slate for each instruction. Clear it right after the cycle check before fetching the new opcode. Makes sense to me. I think as long as it gets cleared before like grabbing the new operands, I think it doesn't really matter which order, but it does make sense to do it at the end. I agree. It's probably cleaner. Here's how it thinks we should implement it. That's okay. That's right. Whatever, right? What I'm worried about is also registers, as like we do have registers inside the operands. Do we need to care about that when we are storing operands in our instance variable list? I don't think it matters, but let's see what Claude also thinks. So this is like helpful, like with coding with an LLM. I think prior, like I would make these assumptions and then I would go into like a bad place of debugging. But now it's like I get this faster feedback loop where I can just like anything like I'm not super sure of or like I am sure of, I need like someone to kind of like cross check me, which is like this smarter LLM. As if we're aligned, it probably means that it's a decent idea. Probably might want to be careful with that assumption too, because they tend to like agree with you on a lot of things. But if it sounds like it makes sense, and the model is also saying that, that kind of makes sense too, I think you're probably going to be on the right track. So I think over time it has gotten better too. Like they used to agree with you all the time on everything, but now they're like calling you out whether or not that doesn't make sense at all. Yeah, let's just double check to see if we need to consider like the register operands when we're pushing things into the operand value list instance variable thing that we're going to implement. So do we also need to consider the registers when we are pushing operand values into the operand value list instance variable? I don't think so personally. The register operands are there to tell us what to do with the data that does have bytes representing it, have bytes representing it. I don't even know if that makes sense too. It's okay. It'll know what I'm trying to say. And I think that's why I like the bigger models. Like I could just not have to think too hard about what I want to say, as long as it's like the gist, and they kind of just mostly figure it out. Versus like a smaller model, I had to be more precise in my language, and that requires a lot of thinking and typing. Here I can just like go, like I could just speak as if I was speaking to someone else. Okay. So in typical Claude fashion, you're absolutely right. Exclamation point. Register operands like BC, HL don't need to go into current operands because they don't have a bytes field. So they're not fetched from memory. They're just metadata telling the handler which register to operate on. The handler can read that info directly from opcode info operands by looking at the name field. Okay. And so current operands should only contain the actual data values fetched from memory, like an N8, N16, R8, A16, etc. So for example, LDBC N16, operand 0, BC, register no bytes, not in current operands. That's fine. Operand 1 is going to be 2 byte. So that goes into current operands at 0. So okay, so that's okay. The handler would look at basically the name to know that it's BC, and it gets the value from current operand 0, and then execute. I guess it'll just set register, but this is the we don't want to think about this here because that might change. But yes, yes, sounds okay. I am going to scaffold now. Okay, so CPU will need something called operand values, and let's just keep it as an empty list for now. And down here we are going to clear operand values. Okay, we're going to reassign it as empty, and then here where we fetch, we just want to append. So self.operand values.append the fetched byte. Then same thing down here. Self.operand values.append self fetch word being 2 bytes. And let's see if it agrees with this. Is this good enough? Okay. If an exception happens or the loop exits before clearing, you could have stale data. Better clear at the start, so each instruction start fresh. Okay, that's a good point. That is a very good point. Okay, so let's do it like this. Okay, so like this. Yeah. Okay, so now we have operand values that stores the literal values in memory itself. Oh shoot, I forgot those past statements. Yeah. Where are they? Okay, I'll clean it up. It's no effort. Why do I need an LM? Why do I need waste tokens doing that, right? We now have the operand values inside that operand values list. So what's next is we need to be able to understand whether or not we need to execute some specific handler for the opcode. Okay, now I'm going to just sort of check in things so that, because we're in a good state right now, so that we can start the next phase, which is execution. So we fetched, we kind of decoded, I guess. We'll probably need to do that, and then we'll execute. So git commit fetching. Okay, so we've done the fetching. Now let's just talk to Claude again and see what might make the next best sense for the next best thing to do. Okay, so what do you think now? Shall we start thinking about execution? I think we need to remember that we're going to use a map of handlers against the opcodes. I think they're keys. Refer to design.md for that approach. So what I'm wondering is that, okay, we know the opcode. We also know the operand values. What else do we need to know to understand how to invoke the right execution handler with the right values? Is it the name of the operand which corresponds to a register 2? Let's brainstorm and establish some firm understanding. Okay. Okay, the last stuff. Okay. Great question. Let's think through what an execution handler needs. So what we have available, we have an opcode, we have the numeric opcode, we have the full metadata. We also have the operand values. Okay. What a handler needs to know. So let's take a look at this. Our beloved LDBC N16 example. The handler needs which registers to operate on. Okay, so the operand name, the immediate value, if anything, which is going to be the operand values index, and whether to read from memory or register. So whether or not it's immediate. So design approach, handlers parse opcode info themselves. Okay, so they'll just, I would think that it should just take it as a value. Okay, so like an argument. But option 2, you pass both opcode info and an operand handler values to a handler. And this is fine. I actually think that this doesn't need to be an argument. I think it's just opcode info. Option 1 is cleaner because each handler is purpose built for its specific opcode. Which one here? This one? Maybe? Okay. The handler knows the operand structure and can directly access what it needs. You'd have a mapping like blah. So what about operand name to register mapping? For most handlers, you'll hardcode the register since the handler is opcode specific, but for patterns, you might want a helper. Okay. Does this align with your thinking? Should handlers be self-contained with hard-coded logic or more generic? Actually, I am in more of the hard-coded logic one because it is finite. We're not going to expand this anymore. So let's reason with it. Okay, I am actually in this same camp of hard coding some logic into the handlers. Here's why I think that is okay. Since we're writing a CPU, it is not like we are going to expand in the future. So it doesn't need to be a scalable design for the future, it just needs to be scalable for what we have now. Okay, so that's like one reason. The next thing is that, well, we may need the info from operand info at some point. I am not sure when, but I have this feeling we might. So taking option 1 into consideration, would it be useful to also just pass in operand info as an argument? We don't need operand values though, since it is already an instance variable. What do you think here? We can sort of think of this approach as a mix of option 1 and option 2. But I really do appreciate the hard coding logic approach. Let me know. Okay. Lots of typos in there, but again, should figure it out. Okay, so I'm totally on board with your reasoning. You're right. The Game Boy instruction set is fixed and won't change. So optimizing for extensibility is over engineering. Hard coding makes handlers clear and direct. Regarding passing opcode info, I think you're onto something. Here's when you might need it. Conditional cycles. Yep, that's exactly what I was thinking. Some opcodes have variable cycles based on the branch taken, not taken. Handler needs to check opcode info cycles and return the appropriate one. Flag operations. Handler might want to read opcode info flags to know what flags is set. And debugging and logging. Having mnemonic available is useful. So a hybrid approach makes sense. Okay. And in your run loop, basically get the handler based off of the opcode and then call handler with opcode info. So this gives handlers both the instance state, self-operating values, self-registers, etc., and then the instruction metadata that we've gotten before. Yes, it does feel like a good balance. It does feel like a good balance. Okay. So before we forget, okay, this is like a to-do, right? So this is like a fix me, because we're going to actually update this in each handler. Okay. Yeah. Okay. Ready to start implementing? What's your next step? Want to set up the opcode handler's dictionary structure first, implement a simple handler to test a pattern, or something else? Okay, so let's do this. First, just a note. Okay, just a note. We're going to have to actually increment current cycles in the handlers, I assume. So I added a fix me here. Let me know if you think otherwise. Yeah. So option A, return, let's see. Option A, handlers return cycle count. Handlers update self current cycles directly. My recommendation, option A, return cycles. Cleaner separation. Handlers focus on execution logic. Run manages cycle counting. Easier to test. Okay, agree. Option A is good. Let's establish that. Okay. Before we begin on the next step, why not take this time right now and update design.md? Can you update it with our approach to handlers and cycle counting? I think it would be an awesome reference later. Okay, so while it's doing that, just a summary about what we're going to do. So every handler is going to be registered against some dictionary. Each handler is going to have some sort of hard code logic that it knows it needs to operate on some register already. And it can inspect the opcode info for things. And then it will return the current number of cycles. We'll use that result to increment the current cycles instance variable of our CPU. There's gonna be like 500 of these to implement. No way I'm gonna do that. I'm just going to just walk through one example with LLM and then possibly just little by little implement sections, like have it just generate the CPU essentially. So it sounds like it would work, but let's see. Okay, so not sure why this is taking a long time. Is it because of my internet? Something's wrong. Okay, there we go. Guess I needed to figure out whether or not I needed to run the tool or something. So I'll just trust it, just leave it the way it is, and then hopefully it'll eventually finish. I have no clue why it's struggling. This does not look good. But I'll let it do its thing. Okay. Sure. Okay, file write operations detected. Whatever, let's do it. Okay, that doesn't look good. Okay. Uh-oh. What did we do? Um, that was a lot of stuff. Is it because we ran out of context? Is it starting to go crazy? Let's see. Um, what changed? Okay, how we implement each opcode. Okay, this looks okay. This looks okay. State encapsulation, registers, current cycles, operand values, memory, opcodes DB, handler design, handler name, mnemonic. Okay, so this is an example. Wow, it got ahead of itself again. Okay. Um sure. Sure. Okay. I guess it's good for it to, you know, no. Okay. Every handler includes a doc string. Okay. Sure. That is sort of in line with what we talked about, but this is concerning. Not sure why it's taking a long time. But I'm thinking about stopping again for this session. Not going to edit the video or publish it yet. I think we have one more we need to do, and then I'll just try to edit everything together because I know there's a lot of stuff I'm going to throw away. A lot of it is just me waiting, thinking, messing up, and so you probably want to just cut that out. Okay. Yeah, let's just can you clean up the backup file? Can you clean up the backup file? Yeah. This thing is starting to break down on me. Wonder why. Uh why is that? Is it because I'm not paying enough money at the regular Copilot plan? That's that's okay. Let's just check this in and then we'll continue later. Fetching and design of handlers. Okay, we're starting to pick up the pace. That's a good thing, right? So at this point, we have an approach, and we'll just start generating code soon. Okay, so now we have our fetching working. So this time, let's try and implement at least one of these opcodes, just to get an idea of how we're going to be implementing the rest of them. And again, the structure is that we're going to be storing opcodes in a dictionary. And so every handler is going to be associated with the opcode value itself. We have the opcode info already when we decode the opcode. We just look into our opcodes DB, and whether or not it's prefixed or unprefixed, we'll get that opcode info. Now, we had defined the structure of our handlers. So if we look at design.md, how we implement each opcode, you'll see that we have, okay, again, the handlers here with a reference to the handler itself. But each of these function definitions are going to be something like this, right? Def underscore handler underscore name. So this could be like LD, BC, whatever. And it's going to be a method. And it's going to take in the opcode info because we need it for things such as like cycles or whatnot. Basically, we do return the number of cycles executed, but we also need the opcode info because we need to be able to increment the number of I think it was bytes or cycles. Yeah, depending on the cycles, right? Like that's why we return it. Sorry, just refreshing myself. But yeah, we execute a different number of cycles depending on certain instructions where, let's say, if a path, like branching instructions, right? Or jump instructions, where if a path is taken, we increment this many cycles. Otherwise, we do other things, and that will be a different number of cycles. So yeah, good thing that we still have context here. What we can do is we can just try to implement our first opcode. Okay, so let's try to implement our first opcode. I will set up the handlers dictionary. As decided, the key is the opcode value, while the value to each of these opcode values are function, or they're really method references, right? Method references to the handlers themselves. So that I'm prompting just to again get the AI warmed up so that I say I will set up, but basically my intention was to do it myself. And I'll go, hey, remember, it's like doing it right now. Hey, remember, I am driving. You are supposed to be a thing, or be this rubber duck. Don't get too ahead of yourself next time. So it's doing no op right now, so that's okay. I'm fine with that, but next time it should really try not to do stuff like this, right? Like I really don't like it when AI tries to do too much for you. It really is something I don't like. And for the longest time I battled this problem where I tell the large language model, hey, stop doing things for me, and going forward, always get my confirmation. But after some time, it always seems to forget this. So, yeah, next time, always ask for my confirmation. So, just to even like, even it has even forgotten. Like my feeling is that since it's been a while since I've actually been on this thing, it probably has forgotten a lot of things. So, yeah, weird. Anyway, let's see. Yeah, there we go. That's the right one. So, next time, ask for my confirmation. Don't jump the, what is it? Just don't jump into coding right away. I am disgusted by this. Okay. Okay. I want to use strong language so that it can actually remember. So you're absolutely right. I apologize. I get ahead of myself. Start implementing without waiting for your direction. That's not my role here. You're driving. I'm the rubber duck to help you think through things, implement when you tell me to. I should have just acknowledged your plan to set up the handler's dictionary and waited for the instruction on what you want to do. What would you like to do next? Okay, maybe it's because I'm on agent mode too, but I think it's okay for now. Given that these are just this is just like a no op, it's okay, right? Wonder what it changed. It didn't change the unit test. It just tried to test again, so that's okay. So yeah, so handler is gathered from getting the opcode handler off from the opcode handler's dictionary, given the opcode. Check to see if we had gotten a valid handler. If so, then we'll just execute the handler with the opcode info, and then we'll just increment the total cycles based off of the cycles actually used. Okay, that's cool. All right. Maybe I should have. It's okay. We'll think about it later. All right. So next, so we have this, but we want to do more, right? Like no op is cool and all, but see, let's do on prefix. No op is cool, right? But let's actually do something more useful. So let's do the next one. Let's implement 0x01. Okay, let's do the next opcode 0x01. Can you just only implement this and add it to opcode handlers? Let's see what comes out of it. Keep it as simple as possible. Note that it manipulates the BC register. Okay, so yeah, this LD, right? This LD based off of 0x01 opcode takes 3 bytes, and then it sets the immediate value, the number 16, I guess N16, basically 16-bit number, into BC. Now, none of these flags should be affected. Okay. I want to see how you handle things like N16, A16, etc., so that we can generalize. Okay. Yeah, because I want to see how we like read and determine this stuff, right? So, okay, so based on the designed operand values already fetched into self-operand values by the run loop, the handler just needs to load that value into BC and return the cycle count. So that's easy. So the implementation would be like this: LDBC N16, LDBC N16, load immediate 16-bit immediate value into BC, and then we just set register BC to be that value. Yeah, and we just get that value right there from the operand values, which we had already gotten from where is it? Operand values right here. Okay. So, okay, all immediate operands are N8, N16, A16, R8, E8 are just fetch values. The operand type tells us that, well, N16, A16 are 16-bit values already handled by fetch word in the run loop. N8 are 8, E8, 8-bit values handled by fetch byte. So I agree. Now I think about it, the handler doesn't need to care about the naming. It just uses self-operand values, 0, 1, etc. in that order. Yes, that does look right. Yes, that does look right. And the reason why that looks right is because each handler is having some hard-coded logic already. So what I mean by that is that since the logic is already hard coded, we already know ahead of time based off of this handler that we should be expecting like a 16-bit value or an 8-bit value and so on. Yes, go ahead. Just go ahead and implement it now. So we're trying to get to a point where the LLM can automate most of the implementation for us, but we just want to carefully check the first few like at a time just to see if we have the right patterns. So yeah, this first one it's working on. I wonder if I'm gonna exhaust like any of my plan limits. It's just using like the normal GitHub Copilot plan. I think it's like $10, $20 a month for that. So I just wonder. So yeah, that looks right. And again, we get the cycles from opcode info cycles 0. Now, again, we hard code our logic here. So we already know whether or not we expect more than one element in cycles. So let's say if we have like a JP instruction where there are two different types of like two different possible values of cycles that we need to increment, we will know. We will know based off of this hard-coded logic here. Okay, cool. So that looks okay. Now let's do, yeah, so what do you think? Can you look? So like, I guess I keep thinking on the fly, and this is just me programming, and I'm just trying to make it worth it to watch. But now what I plan to do is I'm going to ask the LLM, okay, so what based off of like the opcode JSON, do you think we can scale with this approach now? And if so, let's just implement like all of the unprefixed instructions, right? So I wouldn't say all, maybe like 5 at a time, just to make sure it doesn't start to hallucinate. But let's ask the question first. Like, what do you think? Can you look at opcodes.json and see if our approach is going to scale? Any problems you see that opcode implementation are you see that our opcode implementation could fail. Otherwise, let me know and we can start implementing in bulk each opcode. So I don't know. Maybe let's start with 3 at a time. Check, then increase that to 6 until it like starts to fail. So yeah. Okay, so it has done its analysis, it being the LLM. So looking at the opcode's JSON structure, I see a few potential issues with our current approach. So indirect addressing. Basically, if we're not going to be using immediate values, we need to actually interpret this value as like a memory address. So for example, 0x02 is LDBCA, store A at memory address pointed to by BC, meaning BC will have a memory address. We want to take that value in A and store that value into where in memory the address of BC is at. So our current code only handles immediate operands and self-operand values. We need to handle operands where immediate is false, means use this as a memory address. So then we also have conditional branch instructions, multiple cycle counts. So for example, 0x20 is JRNZE8 with cycles 12.8. We've already designed for this. Handlers return cycles 0 if branch taken, cycles 1 if not. This should work fine. Okay, that's okay. Flag manipulation. Many opcodes modify flags 0 or Z, N, H, C. Values can be Z set based on result, 0 clear, 1 set, and unchanged. We haven't implemented flag handler yet. This will need to be added to handlers. Okay. So register to register operations. For example, 0x02 has operands BC, immediate false, and A, immediate true. Sure. Let's see. What is it? 0x02. Yeah, right here. So yeah, okay, it's the same one, the indirect addressing. So the operand doesn't have bytes, so nothing goes into operand values. Handlers access registers directly, self get register, self set register. The main scaling issue I see is indirect addressing. When immediate is false, we need to read write memory at the address stored in register. Our current fetch logic only handles immediate operands with the bytes fields. So should we handle this by keeping operand fetching simple, only fetch bytes for operands with bytes field? Let each handler deal with indirect addressing by checking operand metadata and calling self fetch byte, self get register, BC, or similar. So how are we doing this right now when we're getting the operands, right? So we assume bytes, but if we don't have bytes, we probably want to put in some sort of dummy value. If Okay, so you know what? Based off of this, then maybe it isn't the right way to pass in like the value into operand values themselves, maybe we should make an operand object that stores into operand values. So in this case, instead of like storing like values into like an array like 2, 36, and so on, maybe we can store an object where we say value is something, and then maybe say immediate is something, and then maybe some other property to help us out in working with the operand, something like that, right? So then we'll have like a list of this, like this is like 2 elements already, and maybe that'll help us. Like immediate true will tell us that actually this value is a number, right? Or if it's let's say false, then maybe this could be like BC, and then it'll be like, okay, maybe type is like indirect addressing or whatever. I know I'm like chicken scratching right now, but I'm just thinking out loud. So let's get the guidance to the LLM to propose something like this instead and see what it thinks, whether or not that will solve. So I think I have an alternative suggestion. How about instead of storing the literal numerical values into operand values list, we store dictionary objects that represent the operand. Okay, so for example, an element in operand values list could have something like this. Could have keys like this. Values, the value itself like a number or a register name. In this case, immediate, true, false, or type, whether indirect addressing, etc. What do you think? So that's our suggestion. Let's see what it's going to say. That's a really good idea. Instead of just storing the raw values, we can store richer metadata about each operand. This will give handlers all the context they need to handle different addressing modes. So for example, if we have an immediate value, we'll have 0x124, which is a literal immediate value, and 16. We'll also have something like, okay, BC, name, BC, immediate true, type register. So let's see, 1, 2, 3. Okay, so maybe type should be by default number, maybe? I don't know. Indirect register. So BC, immediate false, name BC, type register indirect. Then we'll also have like a address value. Okay. So then we can assume then that, well, if it's an N16, we don't care about the type, right? But yeah, let's see. So the handler can check the metadata, know how to use operand. If it's a register name and immediate equals true, use self get register operand value. If it's a register and immediate equals false, use fetch byte. Okay, so if it's a register and immediate is not false, fetch byte at this. What is it? I don't understand that. Oh, okay, yeah. No, it says the value inside is going to be the address. Okay, yeah. Okay, so if it's a numeric value and immediate is true, just use the value directory. And if it's a numerical value and immediate is false, use it as a memory address. Okay, so this makes the operand fetching logic and run more complex, but handlers become more uniform and self-documenting since they have the context about each operand. Should we refactor the operand fetching and run and build these dictionary objects instead of just storing raw values? Yes, but can we also account for the fact for that we always want every element in operand values to have uniform keys? So for example, in your example, you did not include type for N16. What do you think it should be? So good point about uniformity. Every operand should have the same keys for consistency. For N16, I think type should be called immediate since it's a literal numerical value fetched from the instruction stream. So the complete uniform structure would be N16 and 8E8 R8 and A16 should just be type immediate. So register immediate, okay, will be immediate true. Type register. Register indirect will be immediate false. Okay, so these are all the different types. Okay. What? Okay, wait, actually think about it more. Should we distinguish between different kinds of immediates? Yes, that's what I was thinking. Just keep immediate. Because immediate right here is not clear, right? You could either have like a number immediate or an address immediate. So, to me, it is quite obvious. It's quite obvious that immediate values should be distinguished as immediate value and immediate address. Okay. Claude really likes to say, you're absolutely right. Because the distinction is important because immediate value and 8 and 16E8 R8 are used directly as data, like load this number into BC. An immediate address A16 used as a memory address, like read from this address. So the uniform structure would be N8 or N16 and 8E8 R8s will have immediate values, and A16 will be immediate address, and it will have the two types of register runs. So if this makes it clear how the handler should interpret each operand, should we pursue refactoring operand fetching logic and run to build these dictionaries? Yes, let's take it a step at a time. Let's fix how we add values into the operand values list. This time to take in to have each element be a dictionary with those keys. We should also document the different types in at design. Oops, I said pound design. Pound design.md. So we want to document this note and other useful things we have just discussed here. We don't want to willy-nilly invent new undocumented types for operands. Okay, let's see. Okay, so good plan. Let me break this down. First, let's document the operand types in design.md. Oops, sorry. In design.md, so we have a clear reference. Then what we want to do, let's just change my brightness. Okay, there we go. Then what we want to do is refactor the operand fetching and run to build dictionaries instead of raw values, update the existing handlers to work with the new dictionary structure, update tests as needed. So before I start, let me clarify the complete list of operands so that will support. So we'll do immediate value, immediate address, register, and then register indirect. So then each element inside the operand values will have these types of keys. Yeah, that looks right to me. Yes, this all looks good. Go ahead and run free for this plan. Okay. So now we put the LLM to work after thinking it through a little bit, and I just need to sit here and just wait to see if things turn out the way I think they will. and we'll see. We'll see how it turns out. And if I need anything adjusted or fixed, it's a great time to just ask the LLM to do that and hope that it works. So right now, again, we're in Visual Studio, and I'm using just the built-in GitHub Copilot. I do have Cursor, and I'm curious to try it in Cursor, especially with the new Claude Opus 4.5 model that just came out. Maybe this already has Opus too, but I think in general, based off of what I'm seeing so far, I think Cursor is still better. So let's see if the tests still work. So the tests do still work. And yeah, so it looks like operand values 1 was going to be from LD, basically because operand the first one is basically the register, and then the last one is the register, getting the value inside the register A and treat it as like an immediate value. So take the literal value in A and store it into BC. So that should be what it is trying to do. So yeah, what I'm looking at the wrong one. Maybe I think I'm looking at the wrong one. I am supposed to look at this one. Yeah. Okay. Regardless, it looks, fetch with operands. That one is failing, but I think it is just because there needs to be some sort of updates because there's no handler implemented. Maybe there should be like a mock one, but whatever. Okay, so it's just gonna manually add these handlers. But I think that's dangerous because we haven't talked about how to update flags yet. But let's just let it go and then see what happens. Okay, it's passing, but I have no idea what it's doing here. Okay, all tests work. Okay, great. Okay. Okay, so are we really ready to scale? We'll see. Okay, so fetch and construct operand dictionaries. That's fine. That's just a comment. Operand immediate. It's going to be operand immediate. So whether or not it's true or false, and then the name. Operand has data to fetch from instruction and stream. Okay. Then we are going to fetch the value. So fetch value is stored. And then we have to determine the operand type. Either it's immediate address or immediate value. So that makes sense. And then we'll just append there. But then also if we have, let's say if, in this case, if we don't have bytes in operand, we can assume it could be some sort of register or register indirect type of operand. Okay, so that's okay. And then here's like the design. Oops, I probably just accepted everything and not care about what these are doing. Dangerous? I don't know. So LDBN8, what is that? LDBN8, which is going to be 0x06. So we'll just take a look at that here. So LDBN8, so this is actually an immediate value and N8 immediate value. So it should just increment things by 8 cycles in this case because it's directly, there's no branching, and then also it takes 1 byte of instruction, so it should be calling fetch byte. So taking a look at that, okay, so operand value does take that first one because 0 is the B register in this case, and we know that it's manipulating B register anyway, so we just hard code that. I will just return the cycles of opcode info. Sure, and opcode info is basically the top level element here. So that looks okay. I'm going to trust the rest because they are sort of similar in its own. So that's great. Okay. Now, do you think we can start implementing things in bulk? Implementing, yeah, opcodes in bulk? Actually, no, we're not ready. Okay, now let's discuss updating flags. So yeah, just remember, so we we're making use of this mnemonic here. We're making use of the bytes, cycles, and operands, but we still need to make use of flags. How do we update flags, right? So looking at the opcodes JSON structure, each instruction has a flags object that defines how it affects the CPU flags. ZNHC, the values can be, well, hyphen or dash would mean that we don't need to care about updating the flags. We just leave it unchanged. 0 means that we have to like clear that flag to be 0, and then it's in the flags register, right? And then 1 means that we have to set the flag to 1. Otherwise, we just set based off of the operation result. Flags are stored in lower 8 bits of the AF register. Okay, so basically the F register, bit 7, bit 6, 5, 4, and then 3 to 0 are unused. Okay. So yeah, we go from in this case kind of left to right here. So some questions to discuss. Okay, so we have 3 questions. Flag update responsibility. Should each handler manually update flags, or should we have a helper method like update flags, blah blah blah, where none means don't change? Flag calculation helpers. Do we need helpers for common flag calculations? Okay, so flag calculation helpers. Do we need helpers for common flag calculations like calc 0 flag to check if result 0, or calc half carry add to detect carry from bit 3 to bit 4, and then calc carry add AB detect carry from bit 7 or bit 15 for 16-bit. Okay, wait. So flag reading, should we just add helper methods like get flag Z and set flag Z to make handler code cleaner? Oh yeah. No, I think flag reading. Okay, so I like your helper idea for flag reading and updating. I think we should aim for hybrid, right? Based on opcode handler. The handler can just call them individually and update them as appropriate. What do you think? So basically we'll just defer to the hand, like given like we have like a set flag, get flag, whatever, we'll just leave it up to the handler to just do that appropriately. So I think that's the right approach. Give handlers the flexibility to call individual flag helpers as needed. Each handler knows exactly which flags it needs to update based on this operation. So we'd have flag reading, okay, flag setting, okay. So common calculation helpers. I'll just leave it to the LM to do that. But yeah, the handler inc B would then just kind of set these flags individually like this. Oh, I guess it'll just determine whether or not it should be set or not. Okay, cool. That's fine. Yes, go ahead. Let's implement. Okay, so now we have unit tests to run. Everything seems to be running. Yeah, 41 tests, so that's okay. Test registers. Are these new ones? Is this a new one? I think this is a new one. No, it's not a new one. I don't even remember anymore. Oh, this is probably our first one. Okay. Okay, so now we want to update the CPU. Or sorry, so it ran the CPU tests and they all failed. My guess is just all this stuff here, these new methods. Let's see. Well, I don't know how it's trying to debug, but to me, it's quite clear that this just doesn't have awareness of these new methods. Okay, we'll run the test again. Still fail. Okay, let's try again. This time with some debug output. I think it's just trying to see how to determine whether or not something is negative. This is actually pretty tricky. I don't blame it. I've run into this similar type of struggle too, like how to tell if something's negative or like overflowed and things like that. So test case is wrong. Okay, sure. Okay. So all tests pass. Let's run all tests to ensure everything still works. Okay, great. So now we actually have new tests. So we have test flags. So that's okay. Alrighty. Okay, so did all the handlers get updated? Let's see. Yeah, okay. So I don't think we need to implement the or I don't think we need to update the handlers right now. I don't think we need to update the handlers right now, do we? Okay. Based off of opcode.json, we don't need to, but we just want to make sure that the model is also aligned with that idea. Yeah. Okay. Yeah, so let's check in what we have right now. So flags and stuff. Or I need to even add all this. Okay, flags and stuff. Okay. So we've implemented just example opcodes already. So now let's tackle implementing. Oh wait, so let's see. Do we have enough to implement all opcodes now? Don't do it. I just want to check before we push forward. Okay, so we have opcode fetching, operand fetching, handler dispatch, register get set, memory read write, flags get set, calculation helpers, and cycle counting. Okay, so we still need stack operations because we do have a stack, so we need a push word. Okay, so and basically it's a wrapper around our memory. We just need to be able to update the stack pointer appropriately, and then pop word will well, we need a decrement if it's a push because the stack grows downward, and then we'll increment the stack pointer by 2 because it all works in 16 bits, I guess. Special addressing modes. Some instructions use HL high and HL low, I guess that's what it means. Indirect HL with auto increment decrement. High RAM addressing. High RAM indexed by C. So this is just offset. Okay. Interrupt handling for enabling and disabling interrupts. Might need interrupts enabled flag. Halt, stop, special CPU states. Okay, whatever. Let's do stack helpers. Yeah, let's just add the stack helpers. Yeah, let's add stack helpers and add a new test file for it. So yeah, let's just have it do that. It seems to know what it's doing now. So we're flying at this point. And then we'll have it write a entirely different unit test file for it. So we can just manage code correctly. And plus it keeps things small so that in case if the LM needs to refer to it again, it doesn't get lost in the context. Although I like argue that maybe our GPCPU.py may grow and might give the LM a hard time in the future. But we'll see. Okay. Yeah, and that's the one thing about like coding with an LLM is that you have to manage context because these things like when things get really long, they do start to get lost in their sea of tokens. So we have a stack test. So we have things like pushing a single word onto the stack. We always check the stack pointer at the end, right? When we do a push. So we start the stack at this address right here. We'll push something. It should be 2 bytes less. Okay. Pop should be 2 bytes more. So FFFFC. Okay. Yeah. So when we pop set value, how do we know 0x34? Did we pop? We didn't pop, right? Oh no, this is just initializing the stack. Okay. Got it. So this is just like mock initializing. Okay, I'll just trust it. I'll just trust it. Okay. Okay, so stack helpers are now implemented. Okay. Let's just add. So git add dot git commit stack helpers. Okay, so this is all I'm going to do today. Just just keep things small, and keep my motivation up. Yeah, I think next we'll probably want to yeah, we'll just keep this chat up, and then we'll continue next time. I'm still gonna like compile all of this into like one single video, so maybe you might not even notice, but you'll probably notice when the date and time. So anyway, see ya.